See? Hello everyone. Good evening everyone.
Good evening, sir.
See, in the last class, it means yesterday's session we have finished D block now. So F block we haven't touched. Okay? Listen. So we'll complete F block elements. Try to listen the class very carefully. You can directly get at least a minimum of one question from this. Okay? See, first thing, what is the general electronic configuration of F block elements? Tell me. Tell me, what is the general electronic configuration of F block elements? N minus 2 F 1 to 14, N minus 1 D 0 to 1 NS 2. NS 2. It is not 1 to 2, it is 2. Okay. So this is the general electronic configuration of F block elements. Okay. And after that we have two series of elements like lanthanides, actinides. Lanthanides, actinides. Now tell me, lanthanide belongs to which series? I mean which group? Both of them are belongs to third what? Third group. Third B group. Okay? Or simply I can say third group. Okay? And which period lanthanide belongs to? Sixth period. Which period? Sixth period. Okay. Now what about actinides? These are also belongs to third B group, third B group and seventh period. This is the first thing. So it means all F block elements belongs to same group. What is that group number? Third. And lanthanide belongs to sixth period, seventh period. Okay. And these elements are silvery white metals, silvery white soft metals. What they are? Silvery white soft metals. Okay. The next one here. Here how many elements are there? Both of them are 14 and 14. Here all are non-radioactive. What I am saying? All are non-radioactive except promethium. What is that? Radioactive element is which one here? Promethium. Here all are radioactive. Okay. Now what is the source from where we can extract these lanthanides? These are extracted from monazite sand. What is that? Monazite sand. Okay. So lanthanides comes from where? Monazite sand. Along with this, in monazite sand, along with the lanthanides, we have approximately 10% of thorium. What we have? Approximately 10% of thorium. Okay. So here thorium and uranium are naturally occurring. What they are? Naturally occurring. Remaining are man-made. What they are? Remaining are man-made. Okay. So remaining are man-made means they are synthetic elements. What are the naturally occurring in actinides? Thorium and uranium. Next. the elements after uranium. What is the atomic number of uranium? 92. Elements after uranium are called what? Trans uranides. Okay. Now what are the points to be remembered here? All third group elements are, lanthanides are third group elements. Actinides also belongs to third group. Period 6th, 7th. These are non-radioactive except here radioactive. Here monazite sign. And here thorium and uranium are naturally occurring. Okay. So thorium, what is the source of thorium? That is also we can say monazite sign. Along with monazite sign, you remember it as pitch blende. What is the next one? Pitch blende. That's it. See what I told you, the first line, these are silvery white soft metals I mentioned now. So softness decreases as atomic number increases. So what I am saying, softness decreases as atomic number increases. It means lanthanides, first here lanthanides here now. So it's as we go from left to right, what happens to the softness? Decreases. So it becomes harder as we move right side. Okay. And here samarium is there now. So the hardness of samarium is almost equals to the hardness of steel. What I am saying? Hardness of steel. Hardness of samarium is almost equals to what? Steel hardness. Okay. Remember this. Up to here everything is perfect. Yeah. Next thing is, let us write general electronic configuration of these lanthanides. General electronic configuration we already written. Now what are the elements we have? Lanthanides. What are the elements? Starts from where? Like 57. Lanthanum, it means all lanthanides present between lanthanum 57 and 72. What is that 72 element? Hafnium. So in between these we have lanthanides. It means from where to where? From 58 to 71. Okay. Let us write all these elements. So the first element, so what is the first element of lanthanide series? Cerium. And last element is lutetium. So 58 cerium, lutetium. So now let us start it from lanthanum itself. But lanthanum belongs to which group element? Which block element? D block. 57. So now what is the nearest atom, noble gas we have for lanthanum? Here it is 54. What is that? Xenon. 54 is done. Okay, after that still how many electrons to be filled? 3 more. Okay, so that is 4F 0 5D1 6S2. So 57, 54, 55, 56, 57. Done with this? Yeah. The next one. Tell me now what are the lanthanide elements we have? Lanthanum, cerium, praseodymium, neodymium, promethium, samarium, europium, gadolinium, next terbium, dysprosium, holmium, next erbium, thulium, ytterbium, lutetium. So now how can you remember this without looking into the books? So I told you now that word, what is it? Lacina is pretty and Pramod, Samir, Europe, गाड़ी में, like गाड़ी में, ticket, देखकर, लिया, तुम भी ले लो. Okay, you can remember with this. What is the first element? Lanthanum. Lacinum, lanthanum. Next cerium, no? Cenum. Next pretty, praseodymium. Next and, neodymium. Next pramod, promethium. Next samir, samarium. Europium. Next, where we have completed? Europium. Gadi, gadolinium. Ticket, terbium. Okay, up to here it is done. Next, Decker, dysprosium. Next, here itself H is there now, holmium. Next, erbium. Next, thulium. B here we have, it is YB. Here we am writing it as B, that is YB. Okay, and last one, lutetium. Like this you can remember. See, first of all you need to remember them. But if you have any confusion or if you felt missing somewhere some element, this trick will be useful. It will help you like a catalyst to remember. Yeah. So now tell me, what is atomic numbers we have for this? 58, 59, 60, 61, 62, 63, 64, 65, 66, 67, 68, 67, 68, 69, 70, 71. Perfect? Okay. Let us write their electronic configuration also. Write with me. So cerium, xenon, next 4F, 1, 5D, 6S2. Oh, okay. So look at here. What I should write here? See, 0 is over now. Directly you write for xenon as 0. I mean directly 2. For which one? F2, D0. Next one. What is next? Xenon. Next this one? 4F3, 0, 6S2. Next. Xenon, 4F4, 0, 6S2. Next, 5, 6S2. Next, 4F, 6, 6S2. See, Europe, what is the place we are going? Where this Lacina is going? Europe. So, Europe is a stable place. Stable place means you can remember it as half filled configuration. What is that? F7 we are saying now, half filled. You can remember like that. The next 6S2. Okay. Since Europe is stable place, gadolinium also wanted to stay in Europe only. So it will also be having 4F7 only. That extra electron goes to 5D, 6S2. Okay. And the next one, xenon. See, remember when we are writing electronic configuration, you won't be seeing F1 electronic configuration and F8 electronic configuration. What are the two things you are not seeing? F1, F8, both in lanthanides as well as in actinides. So now tell me, what is the next number? It should be 8, but this D electron also give it, now what it becomes? 9. So 4F, 9, 5D, 0, 6S, 2. Next one for this you tell me. Xenon, 4F, 10, 5D, 0, 6S, 2. For this one, 4F, 11. This one, 4F, 12, 6S, 2. For this one, 5D, 0, 6S, 2. For this one, 6S2. For this one, 4F14, 5D, 1, 6S, 2. Okay. Now what are the numbers I told you it won't appear? 1 and 8. Now again come from like from the starting onwards. Lanthanum, no F orbital electrons. Next 1, 2. Cerium 2, like the 2, 3, 4, 5, 6, 7, Which is stable place? Europe. In that we will get America or Americium. So that will be the stable place, you can remember. It means Europe and Americium. What is that? Europe in lanthanides, Americium in actinides. Will have half filled electronic configuration. Okay. Next, after along with our Europe, who is we there there with the 7 gadolinium. Okay. So remember, write this electronic configuration first. Completed everyone? Finish it first. See, once after completing the session, you take any PYQ questions of F block elements. You can easily solve. Okay, once you can try after this session. Fine. Done with this, everyone? Please finish it first. How many d orbitals are there in the subshell? 7 d orbitals are there. So it means 7 d orbitals means sorry, what I'm asking? Sorry, F subshell. So in F subshell, how many orbitals are there? So like this we are saying 7, 1, 2, 3, 4, 5, 6, 7. Okay, 7, 1, 2, 3, 4, 5, 6, 7. Okay, 7 orbitals are there in the F subshell. Okay, so now what is a half filled configuration? 7. So F7, full filled means F14. So with this electronic configuration, elements or ions are stable. Yes or no? Okay. So now if you observe this, lanthanum, like all lanthanides, most common oxidation state. What I am saying, most common oxidation state is +3. What is the most common oxidation state of lanthanides? Minimum oxidation state, most we'll be seeing minimum oxidation state as, minimum oxidation state means 0 now sir, means elemental form means 0, it is fine. But with some charge means it should be +2. What is the charge? +2. And maximum oxidation state is +4. What is the maximum oxidation state of lanthanides? +4. So for actinides it will be +7, but now we are talking about lanthanides, so what is the maximum oxidation state it will show? +4. For example, lanthanum, how many valency electrons you are seeing in the lanthanum? First element, I mean this one, 3 valency electrons, na? Remove all the 3, it will be something like this. Lanthanum actually it should be represented as La. Okay, next one, cerium, how many valency electrons you are seeing? 4. So cerium will exist in +4. What is the oxidation state shown by cerium? +4. Not only +4, it can show +4, it can also show +3 also. What I am saying, what is the most common oxidation state of lanthanides? So no matter what is the most stable or most common oxidation state for lanthanides is how much? +3. Okay, now look at here what I am saying. So cerium is there, ma. If I write +4, here I am writing +4. So now cerium +3 means how many valence electrons it has? 1. Okay, +4 means 0. Okay, now tell me for europium, how many valence electrons it has? Like F7, 4F7, 5D0, 6S2. If I remove these 2 electrons, how it will exist? 4F7. It means in +2 it will be 4F7. So this is a stable oxidation, what is that? Electronic configuration. So Europe can show what is the minimum oxidation state? +2. That's why lanthanide showed what is the minimum oxidation state I am saying? +2. Maximum 4. Okay. So now, what is the most common oxidation state or stable oxidation state I am saying? +3. See, now cerium converting from +4 to +3. What it is doing? Cerium converting from +4 to +3. So now what I can say, like a species, like is it undergoing reduction or oxidation? Tell me first. Reduction. Species undergoing reduction means the one which is reacting with this will undergo oxidation. So now what is the name of this compound? Whether I can say it as reducing agent or oxidizing agent? Oxidizing agent, no? So cerium +4 act as a good oxidizing agent. How it will act as? Oxidizing agents. Why it will act as oxidizing agent? Because +4 converts into +3. So during this process it loses electron, it gains electron, the other species will lose electron. So that species is undergoing oxidation now, so we can say it as oxidizing agent. Therefore, cerium +4 compounds can be used in the analytical chemistry. For what purpose? As an oxidizing agent. The best example is a ceric ammonium nitrate. What is this compound called? Ceric ammonium nitrate. What is the use of it? It is an oxidizing agent used in analytical chemistry. Okay. Now look at this europium. Here it is +3 is there. Here +2 is there. So now Europe converting from +2 to +3. Because +3 is most commonly seen oxidation state now. So now +2 is converting into +3 means what is happening here? Is it undergoing oxidation or reduction? Oxidation. It is undergoing oxidation means the species react with this will undergo reduction. So what I can say this as a so you like Europe with +2, europium with +2 act as a good reducing agent. Remember this. These 2 points are very important. Okay, fine. The next thing is, so what is the maximum oxidation state? Maximum oxidation state of lanthanides +4. +4. Done with these 2 things? Yeah, next. Okay, now let us look into the physical properties. I mean, how it will change this, like atomic radius. What happens from left to right in the lanthanides? It means from lanthanum to lutetium. What happens to its size? Decreases. Left to right, size decreases. So what is the reason for this? Lanthanide contraction. So what do we mean by lanthanide contraction? The decrease in the size, due to poor shielding of what? 4f electrons. 4f electrons. What I am saying, decrease in the size due to poor shielding of 4f electrons. What does it mean? Say for example, this is the nucleus of an atom. So this is first orbit, second, third. Let us say here we have a fourth. I mean, this is the 4 orbitals consider. So now 4f means definitely f electrons are here. Okay. Now this is 4f here, let us say. This is 5 and this will become 6. Okay. Now what I am saying is s orbital shape, how you are writing, like a spherical. Like p means it like a dumbbell, like this. When we are going from s to f, s to p, p to d, d to f, what happens to its penetrating capacity, which is symmetrical around the nucleus? S orbital is very symmetrical around the nucleus. If an orbital is very symmetrical around the nucleus, that electrons which are present in the s orbital will effectively shields these outer electrons from this nucleus, like nuclear forces. But what I am saying here, poor shielding of f orbital. It means who is having low shielding capacity and who is having high shielding capacity? Due to its poor shielding capacity, now what happens, these positive charges acts up to nth level. So now what happens, these nth level nuclear forces acting on these electrons means these electrons are strongly attracted by the nucleus. Now what happens to that size now? That electrons are attracted, now what happens to the size? Decreases. So that is what the size decreases in F, like F block elements from left to right due to poor shielding of F orbital electrons. Okay. So you got now what do we mean by lanthanide contraction? Yeah. Now the sizes are looks almost same. I mean very small differences will be there from one to another. In where? Lanthanides. Okay. So now due to this reason, what happens to its basic nature? Like lanthanides forms ionic compounds. What type of compounds it will form? Ionic compounds. Now see, lanthanum upon treating with water, with what I am treating? Water. So it will forms lanthanum hydroxides. What it will forms? Lanthanum hydroxide and H2 gas will be released. So let us say we have lanthanum hydroxide to lutetium hydroxide. So they will ask, like, see, if I say sodium is reacting with water, what is the compound formed? NaOH, sodium hydroxide. We know sodium hydroxide is basic or not. So lanthanum hydroxide is also basic. But they will ask which is more basic out of this. How can you answer these? See, do you remember Fazan's rules? What are the Fazan's rules says? How the cation should be? If small size cation, more positive charge, more will be the covalent nature, less will be the ionic nature. See, which is smaller ion here, lanthanum or lutetium? Lutetium is small now. So if it is small, that hydroxide ions have more covalent nature. If it is more covalent nature, that OH minus won't come out. Because if it is having ionic nature, it can come out easily. So which which compound will give OH minus outside easily? Lanthanum. So now what I can say from left to right, basic nature decreases. So you can say basic nature decreases from left to right. Okay, so which is more basic? Lanthanum. Like this it will be. So least basic is lutetium hydroxide. Next, which is like, see what is I told you, lanthanide forms which type of compounds? Ionic compounds or covalent compounds? Ionic. So now within the ionic compounds, I am asking about solubility. If a compound is more ionic, it will easily soluble. For example, sugar is there, salt is there. Which will soluble in water easily? Salt. So it means ionic compounds soluble more readily compared with the covalent compounds like sugar. So now saying all of these are forming ionic compounds, it's fine. But which is having more solubility? How can you decide? Same, based on Fazan's rule. So which compound is more ionic, this one or this one? The small cation, more covalent nature, less ionic. This is small cation, more covalent nature, less ionic. So less ionic means less soluble. So solubility decreases from left to right. Is this clear? So which compound, lanthanum halides or compound salts, will be more soluble than lutetium halides? Is this clear or not, everyone? Solubility and basic nature? Right, perfect. Next. Okay. See, this color property, mostly they won't ask. Even if they ask, you can able to answer. See, easy. What is the reason for the color property here? FF transition. In order to show this FF transition, electronic transition, there must be at least one electron in the f orbital and at least one vacant orbital in the higher energy. Then that electronic transition takes place. So now tell me, if I say F0, is there any color possibility for this? No. As respect to FF transition, it is not possible. There are some other reasons we may say, later we'll discuss about that. F14, is it possible now? No. Why it is? Yes. See, electrons are there. Do we have any vacancy? Higher energy levels? No. All f orbitals are filled. So F0, F14. It is not possible because there is no vacant orbital to transition, or there is no electrons in F0. So it is not possible. This is a colorless. So it is colorless. Fine. Next, for F1 and for F13, yes, electrons are there. Transition also possible. But the energy required during this transition is absorbed from IR region. Which region? If it is taken from IR region, we cannot see any color because we will see only colors from the visible region right now. So for F1 to 13, no are colorless. Why? Because the absorption of energy considered from where? IR. Next, for F7 it means half fill. This is also colorless because absorption of energy is considered from UV. So that's why these three things are colorless. First, is this clear? Okay. Now, what are the remaining things we may have? Like these are the all +3 ions I have considered. What are these? All lanthanide. You just arrange them in the U shape. How you are arranging them? U shape. Okay. Start from lanthanum. Okay. What is the middle element? Europe. But here you consider it as gadolinium for getting this U shape properly. Okay. So lanthanum to gadolinium, again go like this, so that you will get lines like this. Okay. So now the species here which are having paired, like this pair of ions will show same color. So first two compounds, like see lanthanum, what is atomic number? 57. See, after xenon, what is the electronic configuration? We have 4f0, 5d1, 6s2. If I write plus 3, how many electrons I should remove? These 3. If it is removed 3, what is there? f0, d0, s also 0. Right now? So do we have any valency electrons for electronic transition? So that's why it is colorless. Similarly, this is f14. Lutetium is f14 because 5d1, 6s2. Remove that 3 electrons. So it is also colorless. Is this clear? Like this, cerium, like this is f1, this is f13. This is also colorless because IR region we have seen. And gadolinium, f7, colorless because it is in UV region. Fine, up to here. Next, remaining ions if you see, it is something like this. GRP, Y, PY. Group or groupie, something like that you remember. Green, red, pink, yellow, pale yellow. What is that? Green, red, pale yellow, pink, yellow, pale yellow. You can remember now? That's it. This is the color of that ions. Which ions? All these are plus 3 ions. Lanthanum plus 3 ions. Okay, next. Standard reduction potential. So for all these elements, reduction potential will be negative. What I am saying, for all the elements, reduction potential will be negative. Negative reduction potential means they act as a strong reducing agents. What they will be? Strong reducing agents. All lanthanums have negative reduction potential. For example, if you take that electrochemical series, like we have seen now, like what we have studied, like that we have studied one big line, do you remember? So which is starting element there? Lithium. So it will be having something like negative minus 2.7, something like that. So more negative means it's a strong reducing agent we are saying now. Like that, all lanthanides have negative reduction potential. So I can say they can act as a good reducing agents also. So now these are acting as reducing agents means when you place them with acids, lanthanides with acids, it is going to liberate H2 gas. What they are going to do? H2 gas. For example, I am treating lithium or sodium with HCl. Now what happens? It will gives you LiCl plus H2 gas. A salt and hydrogen gas is liberated. Similarly, lanthanides also upon treating with acids, you will get lanthanide chlorides like lanthanum salts plus H2 gas will be liberated. Okay, then next, see, from lanthanum to lutetium, what happens to E0 values? Increases. Increases means, first of all, they are negative reduction. All lanthanides have negative values only. But that negative value becomes less negative. More negative, stronger reducing agent. Okay, so from lanthanum to lutetium, what happens? It becomes less negative. So less negative means what I told you, more the negative reduction potential, greater is the reducing character. So who can act as a good reducing agent here? Lanthanum. From here to here, reducing character decreases. Is this clear? So stronger reducing agent is lanthanum. Here it is a weak. Clear up to here? Next. Look at this. Okay, fine. Lanthanides, upon treating with water, what is the product formed I told you? Lanthanum hydroxide. See, here what is the oxidation states? Most common oxidation state is how much? Plus 3, like this. Okay, and plus H2 gas will be liberated. Next one, I am treating this with oxygen. With what? Oxygen. So if you treat this with oxygen, lanthanum oxides. But what is the general oxidation state I told you for these lanthanides? 3. Here it should be 2. Ln2O3. Next one, I am treating with some acid. Let us say HCl only. What is the compound I told you? It will gives you salt. So like salt plus H2 gas. Like here particularly you can say acid. If you say generalized acid, it will be salt. Particularly HCl means it will be LnCl3 type of salt. Okay. Next, lanthanum with nitrogen. See, nitrogen will be with minus charge now. How much minus? Like minus 3. minus 3 because valency electrons of nitrogen are how many? 5. Like what is electronic configuration? 2s2, 2p, 3. So 5 valency, 3 more required. So if I give 3 more, it will become n minus 3. So lanthanum gives the 3 electrons, it becomes plus 3, nitrogen becomes minus 3. Clear up to here? Okay. Next one, sulfur belongs to oxygen family only, no? So same like oxygen, sulfur also forms this kind of compound like Ln2 S3 type of compound. Clear everyone up to here? That's it. Next, what are the elements we have here for actinides? First, tell me list of elements. What are the points I told you about actinides? What is the points I told you while in the first discussion? Third group, 7th period, all are radioactive and up to uranium naturally occurring, remaining are man-made or synthetical. Next, after uranium you can say transuranides. Okay, next. List of elements. See, what is the general electronic configuration we have written for F block elements? Like n minus 2 F 1 to 14, n minus 1 D 0 to 1. That is perfect. If in the option that particular configuration is not there for actinides, what I am saying, that is perfect for F block. Particularly when they say about actinides, actually I can go with this one, n minus 2 F 0 to 14, n minus 1 D 0 to 2, n s 2. So this is for which elements? Actinides. See, as per your book, what is the general electronic configuration given? N minus 2 F 1 to 14, n minus 1 D 0 to 1, ns 2. This is perfect. But if in the option this is not given, particularly for actinides, for which one I am saying? Actinides. If this is not given, only this one is mentioned, means you choose this as your answer. Okay, because you are going to see why this electronic configuration I have written. First tell me what are the elements we have? What is that trick I have given you? Lawrence is a great actor. So I am saying Lawrence is an acting tube. Okay, next what I told you? So he selected for UN PA, some award is there like this. Cool. Okay. Next. BCF, M, CF, EF, MN. So this is what the code word I have given. So it's your wish how you are remembering. But see, what is the first elements of this actinide series? I am starting with actinide, AC. Okay, but this is not F block element. What is the first element? This is 89, the D block element, but thorium is the first starting element. What is its atomic number? 90. Next, after thorium, what we have? Protactinium, Pa. Next, after this, U, 92. Next, Neptunium, Np, 93. Next, Plutonium, Pu, 94. Next, A means americium. What is the element atomic number? 95. Next, curium, Cm, 96. B, berkelium, Bk, 97. Next, Cf, californium, Cf, how much? 98. After this, E, einsteinium, Es. Next, F, fermium, Fm, 99 100th. Next, 101, mendelevium, Md, 101. Next, last one, nobelium, 102. And we have started with one actor name, Lawrence, now that is Lawrencium, 103. That's it. So these are the elements. We got the list of elements. Now write their electronic configurations. So it can be which group it is? Third B and period. So it means 7 is 2. Next here 7 minus 1 6D. 7 minus 2 5F. So 5F 0 61 7S 2. For which one? Actinide. So look at this thorium. Careful, look at this thorium. So this is 5F0 here also. 6D 2 7S 2. Next this one 5F, listen here, 5F 1, what I told you while writing the electronic configuration, you are not able to see F1, 8. So here I should not write 1, it should be 2. If I am writing 2 here, it becomes D1, 7S 2. So this D1 continues up to NP, up to where it will continues? NP. So I am trying to give you as much as like useful shortcuts. It's your wish to learn. Okay. So the next one, this D1 from where to where it will continues up to NP. So now what I should write here? F3 D1 7S 2. Next up to here I am saying now 4 6D1 7S 2. Next here it will disappears. 5F. This one you write here, what happens? 5, 6, 7 is 2. This one, next, see Americium, half fill now, so 7, 6D0, 7S2. Next, this is like gadolinium. 5F, 7, 6D1, 7S2. This one, 8 won't appears now. So now what happens? 5F, this becomes 0 now. 9, 6D0, 7S2. Next, 5F. Next, 5F11, 7S2 I am writing directly. 5F12, 7S2. This becomes 5F, 7S2. This becomes 5F14, 7S2. Last, 5F14, 6D1, 7S2. Clear up to here? See, without knowing electronic configuration, you cannot expect an answer from this chapter in your final exam. Okay. Now, oxidation state. Most common oxidation state. Most common oxidation state. Here also plus 3. How much? Plus 3. Minimum oxidation state again plus 2 only. Okay. Minimums at 0 also possible means possible. With one some charge means it should be plus 2. Next, maximum oxidation state. Remember this. Maximum oxidation state is plus 7. Plus 7. Who will show this plus 7 means? Here you can see Neptunium and plutonium. Who are the two elements? Neptunium and plutonium. So remove all these electrons. 4 plus 3. 7. So Neptunium can show the plus 7 oxidation state and also plutonium. So what is that number I should write here? Plutonium. Okay, these are the two elements should be written. Next, what is the minimum I am saying? Plus 2 means who will show here? See, I can remove these 2 electrons from nobelium. What happens? NO plus 2. What is the electronic configuration it has now? 14. So that's why it can show. Okay, plus 3, all elements. All elements will show what is the oxidation state, common oxidation state, plus 3. So most common oxidation state for lanthanides and actinides is how much? Plus 3. Again, basic nature, what happens from left to right? Decreases. See, there it will be lanthanide contraction, here it will be actinide contraction. But which is more means actinide contraction is more than lanthanide contraction. See, there is something called oxocations. What I am saying? Oxocations. Oxocations are formed only by actinides. Oxocations are formed only by actinides. actinoids. Okay, what is this oxocations? For example, here I am writing O, like there will be one metal atom like actinides will be there. M, oxygen like O2 with some positive charge on it. See, oxygen with some positive charge, you should call it as oxocations. So MO2 type or MO2 plus 2 type. So these are what? Examples for oxocations. Who will form these oxocations? Only actinides. It cannot be formed by lanthanides. Remember, this is very important statement. Right. Next thing is writing. But sir is waiting outside. Let me finish this. Huh? 1 minute. So what I told you, MO2 plus or MO2 2 plus will be what? Oxocations that are formed only by actinides. Lanthanides cannot. Next, last 2 questions I have for you. Just answer me this last question first. Electronic configuration of europium and gadolinium terbium are given like this. Atomic numbers also given for your reference, 63, 4, 5. So now what is the required answer? What is this? EU means Europe now. So Europe half filled. So perfect. So what is that electronic configuration? 4F7, 5D0, 6S2. Where do we have? This is D1 should be there, gadolinium. I told you this is also stable. Like that only it will stay. Next, after that 64, 65. Directly goes to 9. There is no 8. So first option, perfect answer. Next thing, you try to answer me this one. Incorrect statement. First read the second statement. Cerium plus 4 solutions are widely used as? Perfect only, no? Next statement. Europium shows plus 2 oxidation state. Why? Because it is F7, 6S2. So remove the 2 plus 2. Perfect. Next one. Basic decreases. This is also correct now. So 2, 3, 4 are correct. When it comes to first one, you are sure about these 3 statements. First one, you see all lanthanodes are much more reactive than aluminum. It may or may not be correct. We are not sure. Okay? But not shown by all the lanthanides. So which is incorrect? First statement. So both questions are perfect. So now you can try whatever the PYQs given in the modules or any other PYQ book you can take and solve at least some 15 questions on F block elements. Your 1 mark from this F block element will be fixed. Okay, that's it. Okay, this is about the session. So you can make your notes.